Why does time slow down near a black hole? Imagine you and a friend each have a perfectly accurate clock. You remain far away in space, while your friend travels toward a black hole. At first, both clocks tick at exactly the same rate. But as your friend gets closer to the black hole, something extraordinary begins to happen. From your perspective, their clock starts running slower. Closer still, and every second for them appears to take longer. Near the event horizon, the difference becomes extreme. But why? The answer isn't that the black hole somehow damages the clock. Time itself is behaving differently. To understand why, we have to go back to Albert Einstein. Before Einstein, gravity was mostly understood as a force pulling objects toward one another. But Einstein's theory of general relativity gave us a radically different picture. Space and time aren't completely separate. Together, they form what physicists call spacetime. Mass and energy curve the spacetime. A planet curves it. A star curves it even more. And an incredibly compact object like a black hole produces an extreme curvature of spacetime. This curvature is what we experience as gravity. But here's the important part. Gravity doesn't affect only the movement of objects. It also affects the passage of time. The stronger the gravitational field, the slower a clock runs compared with a clock farther away. This effect is called gravitational time dilation. And it isn't science fiction. We can measure it here on Earth. A clock at sea level experiences slightly stronger gravity than a clock high above Earth's surface, so the two clocks tick at slightly different rates. The difference is tiny, but modern atomic clocks are precise enough to detect it. Even technologies such as GPS have to account for relativistic timing effects. Without relativistic corrections, positioning errors would accumulate. Now imagine replacing Earth with a black hole. A black hole packs an enormous amount of mass into an incredibly compact region. The resulting gravitational field can make time dilation enormous. Let's return to our astronaut. Suppose you're watching from a safe distance while the astronaut falls toward a black hole. As the astronaut descends, signals from their clock take longer and longer to reach you. The light they send also loses energy as it climbs out of the black hole's gravitational field. Its wavelength becomes longer. This is known as gravitational redshift. To you, the astronaut appears to slow down. Their movements become slower. Their clock appears to tick more slowly. The light from them becomes increasingly red, dim, and difficult to detect. As they approach the event horizon, you never receive a signal showing them simply crossing it in a finite amount of your distant coordinate time. Instead, their image appears increasingly slowed, redshifted, and faded. Eventually, they effectively disappear from your view. But here's where black holes become truly strange. The astronaut doesn't experience their own time slowing down. Their heartbeat feels normal. Their watch ticks normally. Their thoughts proceed normally. If the black hole is sufficiently massive and conditions are otherwise suitable, crossing the event horizon itself may not produce an immediate local sensation marking a physical boundary. They can cross it in a finite amount of their own time. So who is correct? The distant observer, who sees the astronaut's clock slowing, or the astronaut, whose own clock seems perfectly normal? Both are. Relativity tells us there is no single universal clock ticking identically everywhere in the universe. How much time passes between events can depend on gravity and motion. Now consider an even stranger example. Imagine two twins. One remains far from the black hole. The other travels close to it, spends some time in a region of intense gravity without crossing the event horizon, and somehow returns safely. When they reunite, the traveler could have experienced less elapsed time than the twin who remained far away. They would literally have aged by different amounts. This isn't a machine reversing time. The traveler never experiences time running backward. Instead, the two people follow different paths through spacetime and accumulate different amounts of proper time. In that sense, extreme gravitational time dilation can act like a one-way journey into the future. But what happens at the event horizon itself? The event horizon is the boundary beyond which nothing can send information back to the outside universe. Not matter. Not radio signals. Not even light. Once something crosses that boundary, every future directed path available to it leads deeper into the black hole. This is why black holes connect some of the deepest concepts in physics. Gravity, light, space, and time. And time dilation isn't just a bizarre mathematical prediction. Observations of stars moving near the supermassive black hole at the center of our Milky Way provide tests of relativistic gravitational effects in extremely strong environments. Black holes therefore give scientists extraordinary laboratories for studying Einstein's theory under conditions we could never reproduce on Earth. Yet there is still a major mystery. General relativity describes the gravitational environment of black holes extraordinarily well. But deep inside, classical relativity eventually leads us toward conditions where our current description becomes incomplete. Quantum mechanics, the theory governing nature at extremely small scales, doesn't yet fit neatly together with gravity under those extreme conditions. A complete theory of quantum gravity could change our understanding of what happens in the deepest interior of a black hole. So when we ask, why does time slow down near a black hole? We are really asking something much deeper. What is time? Einstein showed us that time is not an invisible universal clock running identically throughout the cosmos. It is woven together with space, and both respond to matter and energy. Near a black hole, that relationship is pushed to one of its most extreme limits. A second for you is always a second on your own clock. But compared with someone far away, the amount of time that passes can be dramatically different. And that may be one of the strangest truths about our universe. Gravity doesn't just shape where we go through space. It shapes how we move through time. If you like this video, please subscribe to my channel for more space exploration videos.